Greetings, everyone. Today, I'll be presenting my literature review on network security by AI and machine learning, done for SC3030. Modern networks are no longer static. They involve IoT devices, edge computing nodes, and autonomous vehicles, and soon 6G infrastructure. As shown on this slide, this creates huge and rapidly expanding attack surfaces. More devices, more connectivity, and more opportunities for attackers. Traditional security approaches like firewalls and signature-based IDS struggle with encrypted traffic and adaptive threats. They are reactive, not proactive. This is where AI and ML becomes essential. They can learn patterns, detect anomalies, and respond in real time, making them fundamental to defending modern networks. To build this report, I reviewed 6 key papers, each contributing to a different part of the security landscape, such as intrusion detection, IoT security, generative AI threats, and secure 6G and vehicular networks. Together, these papers give a comprehensive view of how AI/ML enhance and sometimes endanger network security. To understand why AI is needed, we must first understand the threat landscape. We still see traditional attacks such as DOS, probing, R2L, and U2R. These form the foundations of intrusion detection. But IoT introduces new threats: spoofing, jamming, malware spread, and privacy leakage. These devices are resource constrained and often poorly secured. Generative AI has opened an entirely new attack surface. Attackers can now automatically generate realistic phishing emails, polymorphic malware, or deepfake identities. This is the first time in cybersecurity that attackers have automation at the same level as defenders. This evolving landscape is why AI-driven security is now essential. One of the most mature applications of ML in cybersecurity is intrusion detection. As shown in this diagram, the IDS pipeline begins with raw network data, followed by pre-processing and feature extraction. The extracted features are then fed into ML models, such as decision trees, SVMs, neural networks, or clustering methods, which classify traffic as normal or malicious. Mishra et al. Highlights an important insight. Different attacks require different features. DOS relies on traffic volume patterns, while R2L and U2R require behavioral or payload level features. Ensemble methods perform best, especially for noisy data, but even they struggle with rare attacks like R2L or U2R. This sets the stage for more advanced ML approaches used in IoT and 6G. IoT environments bring their own constraints: low power devices, heterogeneous hardware, and lack of strong cryptography. But they also generate rich behavioral data, which ML can leverage. The diagram shows how reinforcement learning enables IoT devices to avoid jamming. The device observes the channel state, chooses an action, such as switching channels or adjusting power, receives a reward, and updates its policy. This continuous loop allows the device to adapt to adversarial jamming. The next diagram shows federated learning, a crucial technique for IoT. Instead of sending raw data to a server, which compromises privacy, each device trains a local model and sends only model updates. These are aggregated at the edge or cloud to produce a stronger global model. This enables privacy-preserving IDS and authentication without exposing sensitive IoT data. Generative AI has a dual-use nature. As shown here, the same models can be used to defend and to attack. On the offensive side, LLMs can generate phishing content, malware scripts, deepfake identities, and even bypass safety guardrails through prompt injection. On the defensive side, AI enhances log analysis, threat correlation, vulnerability detection, and SOC automation. For 6G networks, AI isn't just a tool. It becomes part of this network architecture. In the service management plane, AI orchestrates SLAs, traffic forecasting, and policy optimization. In the control plane, reinforcement learning supports resource allocation and anomaly detection, operates in real time. At the data plane, ML accelerates packet routing and physical layer security. Finally, in vehicle networks, we see GNN-based anomaly detection, RL-based routing, and federated learning enabling secure V2X communication. These are some of the most advanced uses of ML in security today. Despite all the progress, several gaps remain. Most models still lack transparency, making them difficult to trust in security-critical environments. ML systems remain vulnerable to adversarial attacks and poisoning. Privacy is fragile even in federated learning, and scaling ML to meet the ultra-low latency demands of 6G is still a challenge. Generative AI must also be governed carefully to prevent misuse. The key takeaway is this: network security must become AI native. ML models are no longer just defensive tools. They are now part of the attack surface, and they must be protected with the same rigor as the networks they defend. With that, thank you.